generality to general oriented cohomology. So the first concept is called formal group algebra. So this notation generalized from the following thing. That is, remember I defined SA to be this symmetric algebra. And actually you have another similar notation. That is the group ring of group algebra. Group algebra over Z. So that's why you have formal group algebra. And it's formally generalizing this notation. So what you start in is, first you start at over the coefficient ring R. And we have this group of lattice lambda. So you can consider this X lambda. So clearly that's a polynomial, that's a formal coseries ring with infinite number of variables. So it's a huge ring. And you formally impose the following notation relations. You want quotient out x0 so that x0 is equal to 0. And the second one is that of x lambda, if the formal sum of the two variables is equal to x lambda plus b. So after this quotient, this becomes a ring, and inside this ring, x lambda plus mu is equal to the formal sum of x lambda and x mu. So that's the formal group algebra. So the notation is this. That's called the formal algebra. So that's another something new. No, it's something new, but is in geometry it corresponds to something that you can imagine, that is HT of point. Of speckle. Okay. Remember I said equivariant cohomology is always a complete ring. So is this one. This is a complete ring. So of course that's not obvious. But so basically this Asmussen maps x lambda to C1 of L lambda. So if you start from any lambda, which is a character of T, then you can extend it to get a line bundle on G mod B, G mod T, and then take the C1. The C1 will give you this element, C1 L lambda. So that's the formal group algebra, and that's the construction. It looks complicated, but actually it's not that bad. For instance, if you look at special case, okay. Then this S, I use S to denote this. Then S equal to this group ring, symmetric algebra. And then you take the completion. Complete at the augmentation idea. Remember you have an ideal sending all the variables to 0. And the kernel of that ideal is called the augmentation ideal. Now you can complete this ring and this ideal, you get the wedge. It's the wedge or smash. Wedge. Smash of this. So then this is equal to this. As basically just mapped lambda to x lambda. Because you see lambda plus mu is equal to x sub lambda plus x sub mu. Because we are talking about additive functions. Example 1, example 2, f equal to fn. Then S is asymmetric with this symmetric group ring. Then you complete the augmentation ideal. So that's a group ring. Again, you can map everything to 0. Then here you have E lambda. That's a group ring generated by E lambda. I should say send it to 0. You should send e lambda to 1. So that you have a map going from this group ring to Z, and then you take the kernel, which gives you an ideal, and complete this ideal. Okay, very similar with this case. And this as Watson maps x lambda to 1 minus e to the minus lambda. For instance, if you look at the formal group plot, it's not a surprise because the formal sum of this is equal to the formal sum of x lambda and x mu, which is x lambda plus x mu minus x lambda x mu. Now, if you replace this by 1 minus e to the minus lambda minus mu, and this to be, you replace it by 1 minus e to the minus lambda, this, so it's this one and that one, you have an identity. So you have this as multiple. So as you can see, in active and multiplicative case, it's not that bad. In fact, in omega 1, omega m, it's a basis of lambda. For instance, you can take the group, the fundamental weights basis. Then S is isomorphic to this R. Omega 1, omega 2, omega n. In other words, there's a Paul series ring with n variables. Of course, this is not canonical because to get this as Watson, you have to fix a basis. You have to fix this basis. For instance, in here you have lambda equals to say B1 omega 1 En omega n, and x lambda is mapped to B1 dot F omega 1 plus F. Cheating here, I should mention the meaning of the notation here. So basically, in this case, actually B1 to Bn, they are just integers. And B1 dot sub F, omega 1 means you take B1 copies of omega 1 and take the formal sum of B1 copies of omega 1. And similarly, you take Bn copies of omega n, and then you take the formal sum of all such things. This is Paul series, and we are inside the Paul series, so we are allowed to do that. So then you have this map, and this map is a nice constant. So, but this is not canonical, but in other words, in a sense, it's useless. Okay, this is constant. It just tells you that if you want to do filtrations, then this is something you can use. In fact, you can define this map. Epsilon, the augmentation map into R sending x lambda 0 I be the kernel of epsilon, and you can consider the filtration I that contains I squared contains I plus 3. Then you can consider the associated graded ring. Say I0 is S. And this associated graded ring actually is a polynomial ring. Again, that's something about the filtration. So if you want to use filtration, that's the one you can use. Okay. Okay. So now let's look at this special element. So we have defined this formal group algebra, and there's a special element. And in alpha. Consider this alpha, which is 1 over x alpha, 1 over x minus alpha. Now what's the meaning of this x sub minus alpha? Remember, we have x lambda for any lambda. So in other words, if you have alpha, you have x sub alpha. If you have minus alpha, you have x sub minus alpha. Now because x0 is equal to x alpha plus minus alpha is equal to x alpha, formal sum of these two. So that's equal to 0. And as I said, the formal group law usually start with x plus y. So that's x alpha plus x minus alpha plus x alpha x minus alpha times g of x alpha x minus alpha. Then it's not difficult to see that. So because 0 equal to this, you can move this piece to the other side and divide it by x alpha x minus alpha. So alpha alpha equal to minus g x alpha x minus alpha. You see, you move these two pieces to the other side, of course you introduce a minus sign and then you divide by this, then you get this one. You get minus kappa alpha. So you get minus kappa alpha equal to g of this. That was kappa alpha equal to minus g of this. That's a Paul series. So in other words, this belongs to S. Okay. Now, again, let me explain the meaning of this kappa alpha when we are talking about additive or multiplicative form. So if f equals to f(a), g actually equals to 0 because additive form of group law do not have this remaining term. So kappa alpha is if f equals to fn, this g equals to minus 1. So kappa alpha equals 1. Okay. And remember I mentioned this harmonic form of group law. In that case, this thing I forgot that. Anyway, we don't need this right now. But in that case, so a priori this kappa alpha depends on this alpha. Okay? But if you have positive form, then actually in that case g equals, I think it's mu2 of g equals g minus 1. Okay, let me check. Equal to equal to 1, g equal to minus 1. Okay? Of course, if you have general form of group law, then you don't have such a nice case. It will be complicated and it will depend on alpha. Okay? But at least this explains to you that why this kappa alpha belongs to S for any form of group law. And in special cases, the kappa alpha is quite simple. Okay? Okay, so now the next part I'm going to introduce normal alpha. So first thing you want to do is you want to generalize the original Zhong operator and the BGG operator. That one was the original version is for this SA, that is the additive case. But right now we are talking about general form of group process. So that's why you have to define this operator on S. So if I give you a root, this is the question of roots. I give you a root, you have this simple reflection. Now you can apply it on X. So again, Y group acts on lambda, so it acts on S. Erase the formal group X, but it wasn't here. So then you have this Y group action. Now you take the difference and then divide it by X alpha. Again, it's not obvious why this is a rational function. So why this is again a Paul series instead of a rational function. But it's easy to do that. You can just do some easy computation again by using the fact that is f of x plus y always starts with x plus y. You use this expression, that's enough to show that this x alpha divides the numerator. Okay. So then again, delta alpha, that's the inner So again, it's R linear. Actually, it's SW is linear. That is, if you have a polynomial, if you have a power series that is W invariant, you can take it out. That's quite easy to see because if you have, say, y times x, and if y is W invariant, you can take out y. Okay. So that's why we can put as W. So that's an inverted. Remember in the original example that you have this delta I square equals 0. So from that you can see that delta I is no longer a automaton, it's always an inverted, but not injective. The same applies here. This delta alpha is not going to be automaton, it's not injective. Then you have totally similar relations. That is delta W delta alpha, W inverse is delta W of alpha, and this is Leibniz rule. So totally the same. Now what's interesting is the next one, delta alpha square. If you take the square, then you get the following. So the coefficient is no longer 0, it's actually kappa alpha. So in other words, if you have additive form of group product, you still have delta alpha square equals 0. If you have this one, then delta alpha square equals delta alpha. If you check your notes, this, so, okay, let me put here, that is Fm, delta alpha square equals delta alpha, you get the 0 type. Again, that's the first considered by Kaufman and Kummer. Now, why that's called 0 hack? That's because it's a specialization of the Iwahori hack. Iwahori hack, if you let the perimeter Q to be equal to 0, you get this 0 hack. So that's why it's called 0 hack. Okay. Now, last one, break relation. So if W equals I1 sine k reduced, then delta. Okay, we denote I sub W to be this reduced sequence I1 I k, and you can define delta I sub W to be delta I1 delta I. Okay, I forgot to introduce the. Now that's for any root, you can define this. Now if you have delta I, alpha I, if you have a simple root, you don't want to put alpha here, so that's why you have be lazy and just put delta I. Okay? So that's what I meant by delta I1, delta I2. And this depends, let's see it in the following, does not depend on I sub W, only if F equals Fa or Fa. So this will depend on I sub W unless you have additive or multiplicative form of group product. Actually, I was cheating here. There's another one which is a bit more general, that's called connected K theory, or in that case the form of group product is this one, and beta does not have to be invertible. Okay, so if beta equal to 0, you get additive. If beta is invertible, you get multiplicative. So this delta I sub W does not depend on I sub W, only if you have this kind of form. Okay. If you have more general ones, then this depends on this choice. That's the Actually, that's the main difficulty that makes our work more complicated. That is, we have this dependence. So whenever we have a reduced sequence, we have to fix it. We cannot choose any reduced sequence. Actually, that's the main reason why Constant Kumar, I think, in their paper, they didn't say the reason, but they said after working on additive and multiplicative form group form, they said it looks like it's impossible to generalize their work. They didn't say why, but I believe that's the reason. That is, you don't have Brillouin relation. Whenever you have a W, you have to fix a reduced sequence. But it appears that it still works. That is, we don't need this independence. We can still define things. Okay, so from the chalk group case, just a brief review that we defined this SA and delta I. Of course, the delta I's are operators on SA, and we defined the delta A's star, and this is chalk group of sigma T. So as you can see, the point is to study this delta I operators, the term operators. Yeah, okay, we call this I the formal term operator. So if you want to study operators, you always have to apply it on some elements, which makes it complicated. So that's why you have this idea of constant Kumar. Actually, I'm not sure whether that's their original idea or whether they studied it. But it's a nice idea. That is twisted product. So as you can see, if you want to study this operator, it involves difference or subtraction. That's okay. The well group action and this divided division by x alpha. So that's why you can consider first this Q. So we have the formal group algebra S. So you can look at the fractions, which formally involve everything. And then you can consider this twisted product. Actually, I'm not sure whether it's this one or I think that's the correct one. It's like this. It's twisted. That's called the twisted product. Okay. Now that's a product. So as module, W is just Q tensor on W. Okay. Is this just a free Q module with basis delta W? Now that's a product, that's a module, and now we want to introduce a product on this module. Now this product is twisted. That is, if you have Q delta W, you have another element Q delta Q prime delta W prime. If you take the product, this product is twisted by this well group action. That is Q W of Q prime delta W W. Of course, technically I should put tensor here, Q prime tensor the delta W prime. But because they look quite different, we lazy erase the tensor. So this product is twisted by the well group. So that's why it's not a commutative product. QW is not commutative because the product is twisted by the well group action. Now, why this is interesting? Because in this non-commutative ring QW, you have divisions. You have these divisions of elements from S, and also you have the well group elements. So because of that, you have this QW acts on Q as follows. You have Q delta W. Now you take another element from Q prime, from Q. This action is realized by this Q W of Q prime. For example, if you define the following element as alpha, going to be 1 over x alpha minus 1 over x alpha delta alpha. Then if you look at x alpha, x on q, then it's going to be 1 over x alpha minus 1 over x alpha delta alpha x on q. So that this piece gives you q over x alpha. And this piece gives you s alpha of q divided by x alpha. You see, this is precisely delta alpha of q. Okay? So if you want to study delta alpha, what you need to do is just look at x alpha. That's enough. Because x alpha has already encoded every information about delta alpha. So that's I think that's a smart way to transform from operators to elements. So you just need to look at elements x alpha. And when you want to look at delta alpha, when you want to look at the operator, you just look at the action of x alpha on q. Again, I first saw this in their paper, but I don't think that's their image. It should be imagined back for much earlier times. Because it involves this work group action, so it's not commutative in this QW. So they are not operators, they are elements. You can find the formal element. So now we just focus on these operator elements. First, we look at the properties of this. First one, xi squared. Now, it's not a surprising fact that this is this, okay, because it's just the operator. So the square is equal to kappa of I xi. And now you want to look at, so q also acts on q itself by multiplication. So you also have this xi. Now, what are the relations between the two types of operators? Xi, q. Again, sorry. Xi is x alpha. That's some simplification of notations. So if you have two elements from capital Q, then you can put it in the outside. This side of Q. And you have some extra term, and this extra term is natural. So this is an element from capital Q that I applied on Q. And this is an element of Q and multiplied by capital XR. So if you look at this hack algebra, you also have this operator. And then this kind of relation is called first-term relation. That's some relation derived from representation of kinetic functions, of kinetic fields. So because QW is not commutative, so that's why Q and Xi do not commute, and to be commuted by this one. Yeah.
Here xi q is delta iq.
Xi? Yeah, Xi is X alpha.
Yes, so xi q is delta iq.
The action of Xi on Q.
Yes.
But that one is not the action. That's the product. So because X alpha actually belongs to QW. So I'm talking. So that's why I didn't put product here. That's the product inside QW. Sorry. And so it's this one. So that's another element from QW. So be careful that for the action, now I use the dot. Yeah, and that's confusing. So if you study this, if you define the operators or the elements, special elements, you want to study properties of it. So for instance, you reach the second power, you have this one. So that's enough. Now if you have different properties of xi, xj, si, sj, normally we know this Coxeter relation, that is you raise power of this product, you will get 1 for 2, 4, 2, 3, 4, 6. Just 4 choices. And then, if, let's say if this is 2, then xi, xj, j, xi. If xi commutes with sj, then the xi, xj commutes. That's easy. And sj, or 3 equal to 1, it's more complicated. Then this is equal to xi and xj. So here will be a little sloppy because it's technical and it does not really impact anything I'm going to say. So I just put it this way: kappa ij. Kappa ij are certain elements in S. And actually, I equal to 1 is I equal to 0. So, of course, this is done by some explicit computation actually. The computation of this kappa ij is the starting point of me working in this project. And originally, this definition by Malaga Lopez, Hoffman, Savage, and Zanoni, they compute this kappa ij, but they couldn't show that kappa ij belongs to S. It's not difficult, but they didn't see it actually. And of course, in the remaining part of the work, we have another way to show that such coefficients belongs to S, and then the computation of this kappa ij becomes useful. So it's not really changing anything. So that's the case if you have 3 here. Now if you have 4, then you have xi, xj. Put it here, even though I will not give the full version. Xi, xj. For 4 equal to 1, then you have xi, xj minus xj. Okay, put it this way. So it's linear combination of xij, xji, xj. But there will be no constant term actually. Linear combination of 4 things. So it becomes complicated, and actually what Baptiste is still considering like studying the coefficients appearing in the equations, try to make it smaller, make it more transparent. But so far, I think there's no improvements, no progress. Okay, so as you can see, the relation of the operators becomes extremely complicated. But again, if you have additive or multiplicative form of group problem, not hyperbolic, just additive or multiplicative, then the right-hand side disappears. That's why you have Pareto relation. Oh, that's why you have this independence on reduced sequence. But for general form group problem, you don't have that. As I said, you don't need to worry about the relations. But for one example, that is the hyperbolic form of group problem. Even though the right-hand side do not disappear, but they have some nice form. So if Mij equal to 3, in other words, if this power is 3, then you have this xjij and xij equal to xi minus xj. And the xi is Maybe I think due to the time, maybe I should give the simplified version. That is, any Mij with xji So this bridge relation with linear combination of x, j, I. So I mean, little stop it here because they all look similar. That is, if you have Mij, then this you have Ij, Ij, Ij. Mij copies, and here you also have Mij copies. The difference will be linear combination of such things. And then the coefficient, let me put it as b, because there's just not one coefficient. In front of each term, you have a different coefficient. And from that example, you can see that I put kappa ij. Actually, this kappa ij depends on I and j. But b does, do not, because there's a lot of b, do not depend on I, j if f equals fh. So that's the nice thing about hyperbolic form of the plot. That is, the coefficient is still there, but they do not depend on I and j. This makes some of the computation much easier, and actually this hyperbolic cohomology is, or hyperbolic form of the plot is related to some kind of Young-Baxter equations, solutions of Young-Baxter equations. So that's another story. And that one is related to the fact that b does not depend on I and j. Again, there's a lot of b's, not just one. Okay, so now let's focus on this QW. QW is a coalgebra. In other words, we have to define a coproduct. So let me put this same triangle to denote the coproduct. So sending Q delta W, Q delta W, and so W. So this QW is a free Q module, left Q module. And so this tensor is tensor in that sense. That is, this is a left Q module, that's a left Q module, it tensor over Q. And then you define the delta triangle of Q delta W is this one. Then you can check that this actually defines your coproduct. For instance, if you look at triangle of x alpha, you are going to get the following: x alpha tensor 1 plus delta alpha tensor x alpha. Again, if you look at this piece with this, didn't put this here. The twisted Leibniz rule, not this one. If you check it out, the twisted Leibniz rule is precisely this one. For instance, if you apply this on PQ, then you have x alpha on P times Q and S alpha on P with x alpha on Q. So this coproduct precisely comes from this twisted Leibniz rule. That's not a surprise. And now I said it's a coalgebra, so it should have a co-unit. Coalgebra may not have co-unit, but this is a coalgebra with co-unit. The co-unit is this one. Epsilon. This is the co-unit. Sending all such Q delta W to Q. It's the co-unit. So that's the co-unit. There's one thing I forgot to mention, and that's quite important. That's this one. So, of course, after this I will consider the dual, but before the dual, we need to define the formal alpha number 2 algebra. F is defined to be the subalgebra generated by S and X. So that's an element in QW, and S is a subset, subring of QW, the subring generated by such things. Now, because you have this relation, so you see this is not a commutative algebra. It's not commutative. So that's the formal affine dimensional algebra. So this one we call it structure theory. That's the, this is an important theory, even though it's not applied many times, but it settles down the structure of this formal affine dimensional algebra. That is, df is equal to z equal to w, such that z dot s. So this affine dimensional algebra is precisely the set of elements that preserves S. Okay? We know QW x on Q. X on Q. Now you have S here. S is a substring of Q. So QW, of course, elements of QW, some of them will preserve S, some of them will not. And then EF consists of precisely the elements that preserves S. Okay? Remember we mentioned that Xi preserves S. Xi acts on S just by this rule of theta delta. The delta I preserves S. And now this collection precisely gives you all such things that preserves S. So that's why it's called the structure theory. Actually, using the structure theory, it's very easy to show that all such coefficients belong to S. So with the structure theory, you don't need to really do any computations. Because at the beginning of the work of Hoffman, Monaghan, Lopez, and Savage-Bernoulli, they tried very hard to show that coefficients belong to S. Because you want the coefficients to be Paul series instead of fractions of Paul series. But they didn't succeed actually. But with the structure theorem, this makes this question trivial. Yeah, should mention this is done by Kami, Sanduni, and myself. Of course, Cosmo-Kumba, the original additive and multiplicative case, they have a version. They have a different proof actually. Works for cosmology case, but just in additive and multiplicative case. And for our proof, works for finite proof system and any form of control. Okay, so now from here I can talk about the dual. So first you consider the dual of QW. That's a free left Q module. So you can consider it's dual. Of course, it's again a free Q module. It's a Q module. Because you have Q here. Okay? So you can induce a Q action on the target. Another way to see that is this dual is precisely the set of maps from the set W to the set Q. And now Q acts on this Q, that's why you have a Q module on this set. Okay? So that's the original definition, but it's not difficult to see that they are the same by the definition of QW. QW basically is just W copies of Q. And if you take the dual, it just consists of all the maps from the set W to the set Q. Okay? So that's why you have no such group. It's just you consider W and Q as sets. And of course, then you have this characteristic function Q, in the sense that Fw of V is just equal to W. If W equal to V, it's 1. If W not equal to V, it's 0. Okay? So Fw is a basis of W star. Moreover, because so that's a free Q module. Now you can have this component-wise product. That is Fw and V. If W equal to V, it's just equal to Fw. If W not equal to V, just get 0. Component-wise product. And of course, this product is commutative. So after that, you see that W star is a ring with unit. Now, what's the unit? Take the sum of all such characteristics.
So for the basis of QW dual,
Yeah.
W are parameterized by
Oh, yes.
W.
Yes, okay. And actually, this is a ring, commutative ring with unit. And this product is clear, precisely this one. That's a coproduct. If you dualize it, you get product. Totally the same. Okay. So as you can see, if you work inside QW star, it's super easy because the product is quite explicit. So that's QW star. You can define SW star. But before that, I didn't define SW, so let me define it. So you, SW is just you replace Q by S. So with basis and delta W. So that's a free S module instead of a Q module. That's a free S module, and of course it's containing QW because QW was Q twisted by RW. There's no difference except you change the coefficients. So similarly, you can apply SW star. And the SW star again, you can look at it instead of QW star because okay, that's all the maps from W to S, all the maps from W to Q. So there's no difference between the two except the coefficients are different. Then we can start to define this EF star. There's one thing sorry, let me put as a corollary. That is, EF is a free S module. You put left with basis xi sub w. Now let me explain the notation. So as I said, the x sub, the xi, the two elements, formal two elements, do not satisfy Bernoulli relation. So if you, for each w, if you choose a reduced decomposition, xw will depend on this reduced sequence. Okay, but even though for that case you can still, for each w you can fix a reduced sequence. Then you have a reduced sequence and you can define this. So for each w you do that and take this correction. Still, this gives you a set indexed by one group, and this set will give you a basis. That's a corollary of this structure sequence. Okay. For instance, like the baby example, A2 case, you have E, S1, you have two generators. So you have S1, S2, S1, S2, S2, S1, and also have S1, S2, S1. For the previous elements, this one, you just have one reduced decomposition. For the last one, you have another, you have two. That's S1, S2, S1 is equal to S2, S1, S2. Because in A2 case, you just have two generators. Okay? Actually, in this case, you have the symmetric group S3. Okay. So, for instance, in that case, so all you need to do is you choose a reduced decomposition for each Y group. For instance, for this one, you just choose that one, and then you get 6 elements, and you can define capital X, and then you have a basis for E sub F. Okay. So, because it depends on the reduced sequence, so that's why usually we put I sub W to emphasize that. And then DF is a free S module with this basis. Now, if you take the dual, we can define the dual. Define the dual of DF. That's a free S module, so you can consider the S dual. Then this actually is containing SW star. So then we have the following theorem. That factorize this. So df star containing SW star containing W star. And F star is equal to F of Q. So from now on, I will use Z to denote elements from Q sub W and F to denote functions in QW star. So we know that you have P sub F inside QW and rep S inside Q. And so a function F means you have something from QW star going to Q. And df star consists of precisely all such F that it maps this df into Z. Okay? This one is not difficult actually. You just need to use the structure 0. After you have this, you have that description. So this gives you a description of this df star. And okay, the last theorem today. Let's contact T. The rest is like this. GKM model, which says that df star, so you have another description of. So this describes the all such F F such that F maps df into X. Now there's another description because QW star has a basis FW. So everything inside QW star can be written as a linear combination of FW with coefficients in Q. Coefficients in Q. Now, then you have this description, which says that this consists of all such things, QW, W with Q, W in W, QW in S, such that QW minus Q, S alpha W, divided by X alpha, belongs to S, for any alpha. Find a root alpha. So, to be honest, I didn't know the importance of this description until that I see that in Cuba calculus they use this a lot. Because it gives you a description of all such coefficients of this linear combination. Okay? So that is so clear. And we know df star is containing SW star. That's why the coefficients can be taken to be elements from capital S instead of from capital Q. Now, it can, because this is a proper inclusion. So, this Z does not work for, QW cannot be anything from capital S. Instead, they should satisfy this description. Okay? Actually, from simple calculus, they even get some kind of diagram. For instance, if you have E, S1, S2, S1, S2, S2, S1, then they use graphs to denote like that's alpha 1, alpha 2, something like that to describe the this condition, and then they use combinatorics to study another experiment. But the point is, we have a proof of this one. Again, it's CCC by using purely algebraic language, and this generalized. So for Chow group and K theory, this is already known. We give a uniform proof, algebraic proof. Okay, the time is up. I will continue next tomorrow.